The invention of scanning probe microscopy in the early 80s led to a shift of paradigm in the understanding and perception of matter at the most fundamental level. The motivation was to develop a new microscope that primarily images non-conductive surfaces at the nanoscale. The idea was to measure and control atomic forces acting between the tip and surface at very close distances. The heart of the microscope is a microscopic cantilever with an integrated sharp tip. In very close vicinity, the surface to the forces bend the cantilever. The deflection is measured by a laser, and from this the force can be determined. This here is a replica of the first atomic force microscope. It is in a permanent exhibition called The Making of the Modern World in the Science Museum in London. The first cantilever was made from a micrometer thin gold foil, and the first tip was a fragment of a diamond crystal from an old turntable glued to the cantilever. Not necessarily for a proof of principle you have to build a Ferrari. The whole overall cost for the microscope did not exceed $100. The three-dimensional molecular and atomic imaging of surfaces opened up the doors to the nano world and is now widely used in physics, chemistry, biology and medicine.
So we measure the AFM on single molecules. We can image each atom, get intramolecular resolution. In addition, we can also move the molecule along the surface and measure friction, which is a phenomenon to investigate energy dissipation on atomic scale.
We try to understand how molecules and cells of life interact with each other. Here is a particular application of the atomic force microscope where we measure the weight of the cell, which is important if you want to understand how cells grow into larger cellular systems like tissues, organs or animals.
In our case, we use AFM tips to place individual electronic spins in close proximity to objects of interest to use them for quantum sensing. One particular application is the study of atomically thin magnetic materials, which will form the building blocks of future high-density memory devices.
So we use the high-speed AFM to film biological nanomachines at work, and in particular we're fascinated by the molecular machinery that regulates transport in and out of the cell nucleus.
Our team applies AFM technology in clinical diagnostics. We can detect bacteria and antibiotic resistances in sepsis. The sensitivity of our device is in the range of 10 bacterial cells per milliliter blood.
I'm still curious. I have a passion for knowledge, I guess. It's very stimulating with all the brilliant minds here at the SNI. Exciting science and fun.